Welcome back, everyone, to the last talk of this session, which will be by Pernak, who will talk about quadratic equations. So, when you're ready.
Yes, thanks, Alex. So, first of all, I'm very happy to this year be able to participate in World of Groupcraft. I already wanted to last year, but I couldn't get the appointment to go. So, yeah, I'm quite happy to have the opportunity now. Yeah, as Alex already said, I'm going to talk to you about quadratic equations. More specifically, as you can see in the title, about quadratic equations of wreath products of abelian groups. What these things are, I mean, other than abelian groups, which I suppose you are familiar with, I'm going to explain soon. Everything that I'm going to talk about is joint work with Ruiwen and Jan-Philipp Wächter. Okay, so quadratic equations or group equations more generally are always defined relative to a group. So let's fix a group G and a finite set X, which we're going to refer to as our variables. Then a group equation is a word in the free product of the group G with the free group F over the set of variables. So just any word in this group. Then a solution to such a group equation is a word is a homomorphism from set free product into the group G. So I mean, I'm assuming you are familiar somewhat with free groups. So in particular with its universal property. So specifically, I'm looking for a homomorphism that fixes the group G and that fulfills that the image of my equation W is the trivial element in G. Meaning, as I said, by the universal property, this is just a choice for each of the variables as what you would expect a solution to an equation to be. You're just choosing for each of the variables a value in the group. And well, the equation W equals the trivial element is supposed to be true for that. That's what a solution is. Okay, but the title said quadratic equations. So when do I call such a group equation quadratic? Well, if every variable in the equation occurs exactly twice. Here I'm counting inverses and, well, non-inverse elements the same. So in particular, here's an example of a quadratic equation. You have the variable x, which occurs twice, once as an inverse and once not. And you have two parameters g and h, which are just elements from the group. Okay, I realize now here in this setting I wrote h on the other side, but of course, due to group laws, you can always like write an equation in the form that the right side equals the trivial element. And here I've got a non-example of a quadratic equation. Well, here y appears only once, so I don't call this a quadratic equation. So more generally, what am I interested in? I'm interested in the equation problem, saying if I'm given an equation, W, as a word, finite data over a finitely generated group G, then does there exist a solution? Kind of a natural problem, I guess, for something that you would call an equation. So what do we know about these problems? A bunch of things have already been studied. So I wrote DP1 up here, which refers to, well, what I wrote, the equation problem. So asking for a single equation for a solution. What has been studied is also the Diophantine problem, which refers to a whole system of equation. And for these systems, for example, for abelian groups, it's not hard to see that these equations are solvable, so that there's an algorithm that tells you if a system of equations has a solution or not. Basically, that's equations over the integers. Then we have the same thing for free groups, which is way more involved and has been done in the 80s. So systems of equations over free groups are decidable. There's an algorithm that solves them. And even a step further, people generalized this approach of McCunning to torsion-free hyperbolic groups. I mean, the step from free groups to torsion-free hyperbolic groups is something that I also assume many of you have seen in different settings, and here, well, also the results still hold. Well, for rags, it's also decidable, but we shouldn't generally hope systems of equations to be decidable because actually in most cases they aren't. I kind of put here the extreme cases of free groups and abelian groups, but everything in between is usually tends to be difficult and in most cases might even be undecidable. This is illustrated by the fact that even for some non-abelian free nilpotent group, systems of equations are undecidable. I'm talking a lot about decidability and undecidability here, and I haven't said what that actually means, but I'm also not going to go in detail onto that further. I mean, I could define this using Turing machines or whatever computation model you want, but for today, just keep in mind, well, decidability, a question being decidable means that there is an algorithm that I can, well, program a computer to do that solves the problem. That's the level of detail that's going to be necessary for the talk. Okay, I talked about general equations, but what about quadratic ones? Well, the quadratic equation problem, unsurprisingly, asks, given a quadratic equation, does there exist a solution to W? So it's just a restriction of the general equation problem to quadratic equations. Well, why do we look at quadratic equations? Because of the following lemma. Quadratic equations are nice in the sense that they have a specific normal form. Every quadratic equation can be written in one of the following three forms. Type 1, which is also referred to as a spherical equation. Well, we have a number of conjugates of constants. So in this equation here, the C1, C2, and so on are constants, and the xi are variables. So just the product of conjugates. Then we have the second type, which is the product of conjugates and a product of commutators, only of variables, no constants involved on that side. And the third kind is, well, squares of variables, and then again a product of conjugates. These are the three different types that any quadratic equations is equivalent to. In particular, this is a decidable equivalence, meaning there's an algorithm that if you feed it any equation, it can translate it to one of these three types. So that's why quadratic equations are nice to look at. Now, wreath products, second thing of the title, that G and H be groups. Then G of H is just the formal sums with coefficients in G and indexed by elements in H. I will write them with a capital X here instead of just writing H down there, because this resembles more what I'm going to talk about later, which is polynomials. Our intuition is going to be polynomials here. Well, then the group H acts on these formal sums by just re-indexing, just shifting the exponent, and the resulting semi-direct product, GH times H, that's what I call a wreath product. Okay. Just for, reiteration, then the group multiplication in the resulting group, G wreath H. Well, if I take two elements where the first component is an element in G of H and the second component is an element in H, then the group product according, to the laws of semi-direct products is just, I take F1, I act by H1 on F2 and I sum up the result. And then the second component, I just use the group product on H. So wreath products itself, somewhat complicated maybe, but there's a nice intuition that I like to think about when I'm thinking about wreath products, which is the Lamplighter group. So specifically, the first component G now is just the cyclic group of two elements, and the group H is just the cyclic group. So think of a street with lamps indexed by elements of Z. Each lamp symbolizes some element in a cyclic group with two elements. Well, there you go. I mean, this is very finite, but of course you should think about it indexed over Z. And lamps can be turned on and off. And we have a lamplighter, which now stands there at a specific position over Z. Then each element in the wreath product should be thought of as a polynomial or a configuration of the street, F, and a position of the lamplighter where he currently stands. And then the group product is just, well, we are telling the lamplighter, who already generated a specific configuration and is at a current position, to now, well, just produce the next configuration, so the thing that we are multiplying with. So he walks around the street and turns lamps on and off, or specifically switches the states of the lamps. And he, after that, moves by the translation part of the second element and adapts his position. Well, but we are talking about general wreath products of abelian groups instead of the lamplighter group, right? Or at least that's what I want to talk about. How far does this intuition carry? Well, it does in a sense, because, well, you can surely imagine that instead of a street indexed by Z, you can think of a street indexed by Z squared. So I mean, it's not a street anymore, it's a street grid or whatever you want, or even higher dimensions, not too complicated. Well, I drew some letters, so you can go up and along the street if you want, or the lamplighter can. And, well, what about if we replace the cyclic group in the second component by some more general groups, abelian groups? Well, you can think of it maybe as now the lamps have different states, or specifically, oh, my beautiful picture somehow ended up down there. You can imagine now that the lamps have different colors, say, right? So you're not flipping the lamp state from on to off or vice versa, but you're switching maybe from green to blue to red between colors. So that's a nice intuition I'd like to think about. So main question, can we decide the equation problem for wreath products of abelian groups? Well, quick answer, that's not possible. Recent result from last week, from last year, Ruiwen says, in particular, the equation problem for Z wreath Z is undecidable. It's an undecidability proof of embedding some undecidable linear algebra problem in this group. So this is an undecidable problem. The equation problem for abelian groups hence can't be decidable in general. But, well, on the other hand, we have the result that quadratic equations in the lamplighter groups are decidable. That's already known. Also 24, that was a little bit before Ruiwen's result of undecidability. So there is some hope of, well, some things should be decidable in general wreath products of abelian groups. Well, and the some things are, well, this is among these some things, and the result which we proved, and I'm going to talk about from now on, which is that quadratic equations are decidable in general for abelian groups, or wreath products of abelian groups, I should say. How do we do this? Well, we translate set equations that you saw above into a setting that looks a little bit like commutative algebra. And then we're going to study ideals of things and solve commutative algebra problems. So as a prerequisite for this, some quick recollection. Any abelian group is a ring, right? Any abelian group carries a ring structure as long as it's finitely generated, but, well, all my groups are finitely generated, so that should be fine. And so in particular, it has a multiplication and a neutral element with respect to this multiplication. From now on, usually if I'm working with these abelian groups, I will write plus for, well, the standard group operation, and then multiplication for multiplication in the ring structure. Well, if A is a ring, then in particular A of B, so these formal sums, also become a ring with the folding multiplication that everybody's used to, I think. So hence we can also say what an ideal in such a ring is, which I will be coming back to later on. So I want to look at equations. Equations, as you remember, these normal forms have mostly three different components. They have these conjugates, right? I think they were usually written like z, c, z inverse conjugates. They have commutators of variables, x and y maybe, and they have squares. So these are the three things that we need to study. So let's start with a conjugate in a wreath product of abelian groups. Right? I have an element z and an element g epsilon, which I'm conjugating. So, well, writing that out, nothing surprisingly happens. I'm writing z also in terms of the semi-direct product. And then I'm applying the rule of how inverses in such a wreath product look. Well, you can check this for yourself or just believe me. So this just uses this fact. And then, well, I'm just using the group multiplication law and putting everything together. Now, these are polynomials in A of B, and these are things in B. You can already see that here delta and minus delta are going to cancel. Well, and in the first component, we are just pulling out a factor. So we have f here, and we have f multiplied by x to the minus delta somewhere else. So yeah, we can put this here. So this is what a conjugate generally in a wreath product of abelian group looks like, right? So in particular, I mean, I have products of these conjugates, which will look like this. Well, I've got a product indexed up to n of such conjugates. They are now going to look like something, well, you always see this gx to the delta here for the delta that comes from z. So there's a bunch of gi now that are shifted by or multiplied by x to the delta minus to the I. In the second component, we have just the sum of the epsilon I, well, just coming from here. And then there's f, which is, well, a coefficient originally of 1 minus x to the epsilon, but now in the sum, I'm replacing this by an element, the general polynomial, that's generated by all these binomials 1 minus x to the epsilon, well, more generally epsilon I, where, well, these are the translation parts of the g epsilon I'm translating by. Oh, the constants, sorry. So this is where ideals come into play. So the same can be done for commutators and squares. You get similar terms, but I won't worry that much about this for now. Just let it be said that for commutators, well, I get a similar ideal, but I don't get any translation part. So if I put this together, if I have a general orientable quadratic equation, which looks like this is equivalent, well, or asking for a solution for this is equivalent to, well, finding this f, which is now produced by this commutator ideal and the ideal I had on the slide before, which comes from the conjugates. And this should cancel out the shift of the GI. In other words, well, f is now just an element in this ideal, and I'm asking to move the gi x to the delta I into this ideal. Okay, why is this a decidable problem? Well, there's two components needed. The first is this lemma, which says whenever this equation has a solution, then actually it has a small solution in terms of these delta on the first slide, so more specifically the translation parts of the zi. The lemma states, yeah, whenever this equation has any solution, there does exist a solution, which might be, well, a different one as what you started with, but there is one, which has small deltas in the zi component. And there's a second part, which says, well, asking for if a given polynomial lives in an ideal, or asking for exponents epsilon and ak to exist, that G lives in this ideal, that's a decidable problem. So there's your commutative algebra problem that I was referring to earlier. So why are these two things enough? Well, I'm going to give you the algorithm, or at least a sketch of it, that solves the problem for orientable equations more specifically. So you feed it an orientable equation, and it's supposed to answer yes or no if the equation has a solution or if such a solution does not exist. What do I do? Well, I compute the bound D, which only depends on the GIs. That's an explicit description that comes from the lemma, how to compute this D. And then I just enumerate all candidates for the delta, so for the translation parts of the ZI, up to this bound D. So I'm looking to find a small solution, because I know if there's any solution, there's going to be a small one. And then I'm asking for the solution of this commutative algebra problem. And if the solution is positive, so if the answer to this sub-algorithm is true, well, then I can answer, I have found a solution for the equation. Well, and if I iterate through all of the candidates for the delta I, through the small ones, I mean, and I don't find a solution to the commutative algebra problem, then, well, there is no solution in general, because, well, if there were one, there were a small one as well. Okay, so what I'm going to do in the next or remaining 3 minutes is going to show you how this bound lemma works, so the existence of small solutions. So here I spell it out a little bit more clearly. You have a bunch of, well, polynomials, formal sums, whatever. These are the GI that come from the equation. And, well, there's the technical assumption that they are already like somewhat aligned at the origin, but that's not super important, so let's not talk about it any further. And then there is a constant, which is now specifically computed, but whatever, there is a constant, such that if there exists delta 1 to delta n that shift my GI in the right position, here now I mean the sum is equal to 0, which is going to be replaced later, but equal to 0. Well, then there is a small solution. So there's delta 1 to delta n prime that are smaller than D, which also lead to 0. Okay, what's the proof? I'm going to give you the proof real quick. Well, in fact, I'm going to give you a proof by painting some pictures. And I'm going to paint these pictures in, well, the two-dimensional lamplighter group again. So think of the different GIs as, well, there's some lamps turned on in some places, and which the things which I circled around are the different configurations. And for them to be equal to 0, to cancel out, they need to overlap. Meaning if I'm looking for these delta, I have to, if such delta exist, I'm shifting them somewhere and they overlap and turn out to 0. So where's the small solution now? Well, instead of shifting all these delta thingies over to the far point there, I can also just shift them there, right? And will obtain delta I prime that produce the same pattern, so the same pattern of overlapping of the different GIs, but in a very much in a closer place, just depending now on the distance between the different GIs. Yeah. And then, well, as a last thought, I said earlier, well, I was asking for overlapping now. So, well, I was asking for this to be 0. In fact, the original problem asks not for it to be 0, but in fact to be contained in this ideal, right? That's what the original problem translated to. But, well, the key insight here now is what do these ideals do? I have to basically look at the quotient of A times B. And these quotients are just, well, I'm just quotienting the index group B by the subgroup generated by the exponent of these ideals. And this means nothing else than, well, if B is my index space and I'm forming a quotient of this index space, what I'm doing is I'm folding up this space of, well, maybe Z2 or whatever. So now quotienting by this such an ideal is folding up the street. So in fact, our lamplighter now maybe stands on a torus or whatever, but the problems remain the same. So I think I'll stop here for now and be open for some questions.
Okay, let's thank Leon. Okay, any questions?
So I do have a question. Have you ever seen what is going on quadratic equation in other classes of groups acting on trees? I know that in the Grigorchuk group it has been studied by Myasnikov and some other people. Have you have a look to other classes of groups?
Well, other classes in the sense of
Like GGS, yeah, for example.
well, yeah, I have spent a significant amount of time trying to decide quadratic equations in contracting regular branch groups.
Okay.
Among others, with the technique of these like tree languages.
Okay, I see.
And the intuition coming from the solution of the problem in the Grigorchuk group. Like that's a project I have been looking at. I mean, I haven't gotten anywhere yet, but that's definitely something I have looked at.
Okay, I see. Okay, good.
Okay, there's a question in the chat. Someone's asking, can these ideas be generalized to other equations of special form on lamplighters? So even if they're not quadratic but of higher degree.
So, I mean, there's certainly some equations that you're going to be able to solve that are non-quadratic. Maybe even without looking at these like translation techniques that I was talking about. For example, well, if you look at torsion equations, so just the equation that says x to the n equals 1, is there a solution for such an x in the group? Well, that just asks for what the torsion elements in the groups G and H are. Other than that, I'm sure that well, I can't come up with a specific example, but I'm sure that some easy equations you will be. Ah. Well, yeah, yes. Ruiwen, Corentin just says so. Ruiwen has some results for some general equations. Yeah, of course, and that comes from the undecidability of. I mean, there is equations that are undecidable. But I don't know where exactly this bound starts because I think the undecidability proof has a somewhat complicated equation that then becomes undecidable. So if the shape of your equation is easy enough, you still have plenty of reasons to think it's decidable.